Hi everyone, we are finding area of polar equations now. And so it goes kind of back to where we started with integrals in the first place, but a little bit of review. So area of a sector is going to be the essentially the percentage of the circle that we want. So it's whatever our angle is divided by the angle of the whole circle, which will be either 360 degrees or 2 pi radians. Generally we'll use 2 pi radians, times the area of a circle, which is pi r squared. Right, so if we kind of simplify that down a little bit, okay, so the area of the whole circle in terms of radians is going to be 2 pi. So we plug that in and cross the pi's out. So we end up with 1/2 r squared theta as the area of a sector. So this may seem a little arbitrary to you, but I promise it does come from, again, just percentage of the circle that I want times the area of the whole circle. Okay, so if we want an exact area though, because that works really well for perfect slices, if we want an exact area of something a little more complex, then just like we did with Riemann sums, we're going to want to break that up into sections. So the more sections I break it into, the better the estimate of the area. And so naturally, if we want the exact area, we're going to want to take the limit to infinity. So we have an infinite number of sections giving us the exact area. So same idea as a Riemann sum for our basic integrals that we did before. And so eventually we get to our area, and so our area is given as 1/2 the integral from some a to b, or alpha to beta, of r squared d theta. So r is going to be a polar function in terms of theta, and obviously d theta tells us it's in terms of theta. So let's give an example shot. Right, so they ask us to sketch the graph of this function, find the area. All right, so the first thing I like to do with these is come up with a table of points, okay, especially if you don't feel as comfortable with these functions. I don't know what happened there. All right, so typically easy points to plug in are like 0, pi over 2, pi, 3 pi over 2, and 2 pi. Right, if you plug these into our r function, we get 2, 4, 2, 0, and then back to 2. So if we plot these, so I'm plotting these as polar points. So my angle of 0 with a radius of 2, angle of pi halves with a radius of 4, angle of pi with a radius of 2, and then angle of 3 pi over 2 with a radius of 0. All right, we get something, it's very common to see this. It's a cardioid. So if you get something kind of in an upside down T shape like this, or a T shape like this, it's very common to see this. It is going to be a cardioid. Okay, so I see that from 0 to 2 pi, at 2 pi it starts to repeat itself. Okay, so it'll make the same shape over and over again. So if I want to find the area of this, well, first, I stick a 1/2 in front. Don't forget that 1/2. Okay, I'm going to integrate this from 0 to 2 pi because I know that's when it starts repeating itself. Okay, inside I need to put r squared. So my r is given as 2 plus 2 sine of theta with respect to theta. Right, and we plug that into our calculator, we get 18.849. All right, let's keep going. Next one asks us to set up an integral to find the area of one petal of this function. So that should give you a hint that this is a rose. It's a rose with 3 petals, each with a, I guess, a radius of 2 or a length of 2 for each of my petals. So we set this up that my first petal is in the first quadrant, looking something like that. The second one will go out something like that, and the third one will go down. And again, these should have a length of 2. I drew this one kind of long, but these should have a length of 2. Okay, so, and again, if you want to set up a table of values, that's totally fine. You just be careful with the points that you pick. So if you set up a table of values and you pick the same points that we just did, that's not going to do you a lot of good. So you're going to want to pick smaller points. For instance, like 0, pi over 6, pi over 3. Okay, that gives you a good idea of where this is going to be in terms of your graph. So if you pick 0, pi over 2, pi, you're going to get 0 a lot. And so that's just, yeah, just be careful with that. Mainly because of this 3 right here. So just be careful with that. Anyway, so we're going to want to set up an area equation. Now, typically what we do with petals especially is, so I know that at this angle, which is pi over 6, so if you plug pi over 6 into this, you kind of get you get where the petal is the longest. I know that that angle splits my petal in half. And so if I can find the area of just half of this petal and multiply it by 2, that will give me the area of the whole petal. And that's typically the way that we approach finding the area of petals. So I'm actually going to multiply my area by 2 because pi over 6 gives me half of my petal. And then I'm just going to plug my r equation in and square it. So 4 sine squared of 3 theta with respect to theta. Now, it would be the exact same thing if you said 1/2 integral 0 to pi over 3 4 sine squared 3 theta d theta. Okay, this is the exact same thing. It's just typically with petals, it's easy to find where the length of the petal is the longest, and so we can just multiply that by 2 instead of worrying about the angle, especially if it's a complicated angle. Typically, it's easier to go about it this way instead. But to each his own. It kind of depends on the problem, but typically this is going to be easier to go about. All right. Let's keep going. So again, we want to find the area of one petal of our cosine of 2 theta. And so kind of again, I'm thinking about a value of theta that I can plug in that will give me kind of a maximum value of cosine. And so if I plug 0 in, so cosine of 0, I get 4. Okay, and that makes sense because cosine of 0 is 1. So that equals 4. I have a maximum of 0. And if I plug pi over 4 in, I end up evaluating cosine of pi over 2, which is 0. So I know that if you look at the graph of this, so it goes out to 4. So one petal will look something like that. Hey, what I just found is that from 0 to pi over 4, I have exactly half of one petal. Okay, so from 0 to pi over 4, okay, so this angle is pi over 4. From 0 to pi over 4, that gives me exactly one petal. Okay, there's actually 4 petals on this. It'll look something like this. Something like that, anyway. But from 0 to pi over 4, I find that I have exactly 1/2 of a petal, and that's important. So I want to set up my area equation. And again, because I'm finding the area of half a petal, I need to multiply this by 2, which cancels out that 1/2 in front, so I'm not even going to put it there. I'm going 0 to pi over 4, pi over 4 of r squared. So 16 cosine squared of 2 theta d theta. Right, so just be careful with those 1/2s, especially with these petals. Typically, again, we want to find the area of half of it and then multiply it by 2, so we don't even need this, but do not forget to put it there if you aren't doing it the other way. Okay. Anyway, so that's it for this video. I will see y'all later.